Today, what I wanted to do was do a project with running NuPIC on the Raspberry Pi, and I wanted to be a little bit more than just a Hello World application. I actually want to do something interesting, and my thought was the Raspberry Pi has these GPIO pins, so why don't we make use of those? So we'll do something with NuPIC that uses the GPIO pins on the Raspberry Pi. And I'm going to be using a Pi Zero. This would obviously work better on a 3B Plus or one of the bigger ones, but we're going to do it on the Pi Zero for this video. I have these little light buttons here, which basically have an LED in them and then they're a switch. And it reminded me of that old game called Simon, where it basically plays a pattern and then you have to repeat the pattern. And my thought was that NuPIC would actually be perfect for this, because we could actually do it in reverse, where I do the pattern and then NuPIC is responsible for playing it back to me. So that's what we're going to do, is sort of a reverse Simon project, where I'll put the pattern in and then NuPIC will learn the pattern and have to play it back to me. Alright, so let's get started on this. For this, what I thought I'd do is I'd have a box here, and I thought I'd cut some holes in here, put the buttons in here. I'll probably put the buttons near the top, so I got some room at the bottom to put the circuit. And then I've also got this speaker. It's fairly large. I'll have to fit it in here somewhere, so we'll see how that goes. But basically I want to put everything into this box and then be able to play it. To run without having the cords going everywhere, I've got this, it's called, what is it called? I think it's called the Li-ion battery hat. So basically what this does is you take a lithium-ion battery, and it's just a hat on top of your Pi. This will work on the Pi Zero. It'll also work on the bigger ones. And it powers it for you. And it's rechargeable. It's got a USB-C. You can also charge other things from it, so it's kind of a nice little hat. And it has the pins going through so that you can still wire things up from the hat. So it's kind of a nice little deal. I think it'll work perfect for this project. So I'll go ahead and hook that up first. It comes with these standoffs here, so let me start by putting those on, because I don't want to mess up the pins. If you try to put it on there without the stand-ups, you can bend it and it'll mess up the pins. So I'm just going to put the stand-ups first on here. So those basically go through the hole here. You get these little nuts. We'll put them on the back. See if I can get this. Very delicate work here. My son here is today. He's going to watch and learn today.
Hi guys!
So if he has any questions, he can ask, and then maybe there'll be questions that the viewers have as well, so I'll answer them. And then hopefully this might be a little more advanced. Robbie's done some programming and some electronics, so this will be a little more advanced than the stuff he's done, so hopefully he'll learn something by watching this project. Alright, so we got this standoff on place. I'm going to put one more on the front here. This is just to hold that hat up so it doesn't bend the GPIO pins.
So where did you get these little stands?
Yes, so these standoffs right here, they came with the Li-ion hat, and I got this on eBay. They may have this on Adafruit as well. I'm not sure. I haven't actually looked for this particular one here. This one I got from China. It was cheap, really cheap to get on eBay. It took a while to get here, but yeah, it's a really useful little device. So I've got the standoffs here, and that'll help, like I said, to keep it from bending the pins too bad. So we'll go ahead and install that hat on here. It's called a hat, which I think is an interesting name, because it's sort of like putting a hat on top of your Raspberry Pi. So Alright, so that's in there, looks pretty good. And now they have these little screws to sort of hold it in place, so I'll go ahead and put those in as well. I don't think these are necessary, but let's see where my screwdriver, here it is. But we'll go ahead and put them in just to be thorough here. Okay. And then one more screw here. Oops. Get it in there just right. Okay, and you can see this fits together really nice. It's nice and compact. You still have access to all your ports. You can charge something else on here if you needed to. You can quick charge with this one, or you can do a normal micro USB charge from this one. So this is a USB-C, micro USB. So however you want to do it, it gives you a lot of options. Alright, so we'll put the battery in. Battery goes in on the top. And whenever I first did this one, it wouldn't come on until I plugged the USB-C in and gave it power. But whenever I pulled the USB-C out, then it continued to power from the battery. So I'm not sure if it's going to do that again now. We'll see in a minute here. But if you see that, you plug one of these in and it doesn't come on, then just plug the USB-C in and give it some power to start with. Alright, so we got everything in here. I got my micro USB, or my micro SD card in. This already has Raspbian loaded on it, and I already installed Docker, and I pulled down the NuPIC image already because that takes a really long time, and I didn't want to have everybody wait on the video for that to come down. So I've got instructions on the forum for how to do that, and I'll also put it in the comments below the video. Alright, so let's go ahead and make sure this is working. We'll start by plugging everything in here. Alright, everything seems to be working good. So we'll go ahead and power down. Well, I'm going to wire everything up, and then I just wanted to make sure it was working, everything was in place before I start wiring things in, so I can sort of rule out any mistakes I made with that setup. So I'm going to go ahead and shut down. We'll do the wiring, and then we'll fire it up when we're ready to run to write the program. So we're going to do the electronics first, then the programming. First thing I'm going to need is the pinout, which I probably should have grabbed that while I had it on. So let me go ahead and do that again. Yeah, so I need to have the pinout, so I need to know what these pins are. So let me go ahead and look that up. Plug all this back in again. I should have thought of that. So let's start with the pinout.
So basically, where did you get this dashboard thing?
This one, the breadboard. Yeah, this one I believe I got on Adafruit. You can get these anywhere. These are on eBay also. They're just simple breadboards here. I believe I got this one on Adafruit. Alright, so if you look when you do pinout, it basically gives you some information about the pins, and what we're interested in here is if you hold your Pi like this, this way I guess it is, then the 5 volts are to the right top, and so that's how you line up everything on this pinout. Okay, so I'm going to write down. I'm going to start with GPIO 4. No, actually 2 and 3 are not used. It was they have a resistor on there that's already set to pull up resistor, I believe. Whereas the other ones you can program, and I tend to use pull down, so that's why I don't use 2 and 3. So I'm probably just going to start with 4. We'll leave 0 through 3 alone. We got plenty of GPIO pins to work with here. So the basic circuit that I'm going to do here So on these lights, these are I believe 5 volts. I'm going to actually pull up the spec sheet on these. But you can't run these off the GPIO pin because the GPIO pin actually just puts out 3 volts. So what you're going to have to do is power the 5 volts and then use a transistor like one of these. And the GPIO pin will turn the transistor on, which will allow the 5 volts through. Let me pull up the spec sheet. Basically what we're going to have here is we're essentially going to have plus 5 volts. This basically shows a battery, but you could do this with a battery. We're actually going to do the plus 5 volt pin in our case, but you could do this with an external power supply of 5 volts. So, but in any case, the 5 volts is going to come in. It's going to go into our LED. Alright, and then that's going to go into a resistor. That then goes into the collector on the transistor. The emitter comes out and it connects to ground. And then the base, there's essentially a resistor here. It then connects to the GPIO pin. We got basically plus 3.3 volts. So this is the base, this is the collector, this is the emitter. Alright, so this is the classic circuit for running a load off of that's controlled by the GPIO pins. You got a transistor, you've got your load, resistor to make up the difference in voltage, and then you got some resistor here that's set to allow the load that's needed, the current that's needed for this load through the transistor. Okay, so all we're going to have to do is calculate these resistors here in this circuit. So to do that, what we want to do is first we'll go to Adafruit.
So on your little drawing right here, basically what is the those 3 lines stand for?
Which ones?
These.
These? Yeah, that stands for ground. Yes, that's a good question. It's called ground, and basically, if you're looking at a battery, for example, the plus voltage is coming out of the plus, and then the minus is what they call ground. Alright, so that's whenever you see that symbol, that's just saying ground. Okay.
Okay.
Now a lot of times ground will be attached to like the chassis or something, like if it's made out of metal, the ground will be on the casing. So that basically you want to make sure you don't mix up the plus volt with the ground, or you can short out the whole thing.
Okay.
So yeah, that's just for talking about ground, and then this is 5 volts in to power the device, and then 3 volts to switch whether it's on or off. Okay, so we're going to go to Adafruit here. And then the transistor, Robbie, I don't know if you're familiar with transistors, but basically the way they work is they have something called a collector and an emitter, and the current cannot go through this unless the gate is open. So when the gate is closed by default on the type of transistor we're using, so this circuit will be off until we add a little bit of power to the base here. See the base on this part, the B? We add a little bit of power to that, then it lets the current flow through, and so that'll turn the light on. That's basically how that
It's
works.
kind of like a door in wind. Like when you open the door, a big gust of wind comes in.
That's a good analogy. So yes, the door is blocking the wind from coming in. You use a little bit of force to open the door, and a lot of force can come through the door. Yes, that's exactly what that's like. That's a good analogy. Alright, so if we come down once this loads, give it if we come down, somewhere in here they have, yes, here, we have the technical details. So they're 5 volts at 10 milliamps. So we need to calculate how much resistance we need here. And I just rolled a little bit too far here, so let's go up a little bit. But I need to know how big of a resistor here that I need. Knowing that this guy is using 5 volts and essentially 0.01 amps. That's what 10 milliamps is. So the way we calculate that is you basically see how much voltage you have coming in, which is 5, and you figure out how much voltage you need to eat up besides what it's using. So in this case it's eating up 5, so there's really no more to eat up. It's going to be 0 volts. So 0 volts at 0.01 amps. Trying to calculate the resistance. So basically we can use the resistance equals the voltage divided by the current. Okay? So the volts that we're trying to use up are 0 divided by 0.01. What is 0 divided by anything?
0?
Yeah, it's the same number, right? So this is just 0.
I totally
Okay.
remember.
So in other words, we don't need a resistor here. So that's good. This is going to eat up all the power we need. We don't need to eat up any extra. And again, it can use the full 5 volts essentially, what we're saying there. Okay. So now we need to calculate what kind of resistance we need on this guy here. So here we've got something called HFE. I don't really know what that stands for, but that's called the beta. A transistor has a beta value, okay? And they refer to it as HFE. And now HFE equals the current of the collector divided by the current at the base, okay? Or we could arrange it as the current on the base is equal to the current on the collector divided by HFE. Okay, so any of those we can use. These are just rearranging the same equation. So what I need to know, we know the current that we're trying to do here is 0.01 amps. That's going to be the current on the collector. So what I need to know, in order to determine the current in the base, I need to know HFE for this resistor. So we'll go ahead and look that up. Basically what you do is you need to know the model of your transistor. And it's important to know the actual model, not just like what it's referred to as, because if you, for example, you just look up like 2N222, there's different models that some of them will have, the base will be on one of the pins and the collector on the other, and then the other models will be flipped. So you need to know the model of the transistor that you have. The model that I have is called PN2222A. And we'll do spec sheet.
So a question I've been waiting to ask because I didn't want to disturb you. Why are you basically doing this on the slow Raspberry Pi when you could be doing it on the fast one?
Well, I want to see if it'll work on here actually. This is sort of the low end. If it can work on here, then you know for sure it'll work on the big one. So this is really just prove that it can work on here. Plus it's small and it'll fit in my box nicer. So that's the only other reason. Alright, so we've got our spec sheet on here. This is the spec sheet for this particular model of transistor that I have here. So if you look at a transistor, it has sort of a flat side and a round side, and you need to know where the base and the emitter and the collector are. So you can see here that in this case, if you look at the flat side to the left, then you're going to have the emitter on top, the base in the middle, and the collector on the bottom. So in other words, if I want it to look like sort of the way I have my diagram here, where I have the collector on the top and the base in the middle and the emitter on the bottom, I need to sort of rotate it. So the way I want to be dealing with these transistors on my circuit, just so it's arranged the way I'm used to thinking of it in my head, is I need to have the round side to the left, and what that's going to do is it's going to put the collector on the top, which is where the load is attached, the emitter on the bottom, which goes to ground, and the base in the middle. So that's how we want to wire it in. We need to make sure we put the flat side to the right. Okay? We won't wire it in this way. Okay. The other thing that you need to look on here is we're trying to find HFE. So if you go to what a section in this spec sheet called on characteristics, right here, on characteristics, it has a section where it measures HFE for different currents. And so we're trying to do 10 milliamps. So 10 milliamps is right here. And for 10 milliamps, it's showing an HFE of 75. Okay? So this is equal to the current for the collector over 75. The current on the collector, of course, is 0.01 amps over 75. So let's figure out what that is. So let's pull out our calculator. Let's see, calculator. Okay, so we're going to say 0.01 divided by 75 equals, so this gives us current on the base needs to be 0.00013333 and a bunch of other threes out there. All right, so this is the current on the base. So again, if we can pull out Ohm's law and figure out what this resistor needs to be. First of all, we know that the transistor itself is going to use some voltage. It actually turns out that the transistor uses 0.7 volts. And this is just a standard value of basically every transistor is going to have this value. The normal transistors will have this value. So we're just going to use that at 0.7 volts. So basically what Ohm's law comes out to be is resistance is going to be equal to 3.3 volts minus the amount the transistor is using, 0.7 volts. And we're going to divide that by the current at the base, which is 0.000133333. All right, so the resistor is going to equal 3.3 minus 0.7 equals, okay, we're going to take that and divide it by 0.000133333 equals, all right, and that gives us a resistor of about 19.5 kilohms. All right, now that's close enough. I'm actually going to use 20 kilohms because I've got these 10 kiloohm resistors here. Two of them will be 20. And as you know, I picked the minimum value 75. I put up a little more like 76 or 77. And you run these calculators, and you're going to get over 20 kiloohms. So we can use 20 kiloohms. It's going to be a safe value to use here for each of the lights. Now the last piece is I'm also going to be running the speaker. So I want to actually make some sounds. You can see this speaker is a little bit hefty for the Raspberry Pi. This is just showing 3 watts. If we say we know that watts equals voltage times amps, then we know that 3 watts equals 5 volts times the amps, which means the amps is equal to 0.6. So this is essentially 600 milliamps. Alright, and that is a little high actually for this transistor. If you go up to the top of the spec sheet here, you can see that in the max settings that they used were 600 milliamps. And if you read this little warning down here, it says functional operation above the recommended operating condition is not implied. Extended exposure to stresses above recommended may affect device reliability. So in other words, we're going to be putting this at a little bit of the high end, and we could potentially burn first of all, we could burn the transistor out. We could potentially burn out the pi if we're not careful. So what I'm going to do is, if we actually ran these calculations earlier, because I wasn't sure if this speaker was going to work, what it comes out to is basically no resistor. Well, I'm going to still add a 1K resistor in the circuit here. That means not as much power is going to be going through the speaker. We don't need it to be going full blast anyway. So even if it's a little bit quieter, as long as we can hear it fine, that'll be fine. So we're not going to be running at full power. We don't need it to be blasting our ears anyway. So I'm going to put a 1K resistor, and that should make this a safer circuit for the Raspberry Pi. All right, so that's pretty much all the calculations we need to do. Do you have any questions?
So basically, did this speaker like come with something like the Raspberry Pi or something?
I think this came with another kit that I had. I'm not actually sure what this came with, but this is a heftier speaker. Probably if it were, if I had a little piezo speaker or something that wasn't as big as this one, it'd be better. But this will work fine. Like I said, we don't need to blast this at full volume. We can run it at a lower power, and it'll be just fine for what we're doing. And then we'll keep our circuit nice and safe. Okay, so let's start by, like I said, I'm going to wire up the board before I turn that off, because I might need to look something else up. I don't know. So I'll wire up the board, and then we'll bring in, then we'll turn the Pi off and wire it in. Okay, so we're starting with electronics, and then after we get the electronics, then we'll turn the Pi back on and we'll do the program. Okay, so remember, we're holding it just like in my diagram here, the flat side to the right. That puts the collector on top and the emitter on the bottom. And now remember, in our circuit, the emitter is going to ground. So what I'm going to do is, on this board, I'm going to have the 3.3 volts on this side and the ground next to it. And then I'm going to have the 5 volts on this side and the ground next to it. So what I need to do for this transistor is I need to have the emitter connected to the ground over here, and then the base and the collector, they can be on a couple of rows up on this side, so we can wire stuff to them. So I'm just kind of shaping this so I can fit it in there nicely. So we've got basically the emitter going into the ground here, as you can see, and the collector on the top and the base right under next to it. Alright, so we're going to need 5 of these. So one for each of the buttons. I'm not going to do all 5 of these buttons. I'm going to do 4 buttons, red, green, blue, yellow, plus the speaker. So I need 5 transistors. I'm going to do 5 of them.
So basically, with the transistors and the resistors, if you like bend the little like the little wire thingy on it,
yep.
Basically it still works.
Oh yeah, these can bend up. And normally there's actually a little device that you could plug on top of this. It's called a mini proto board. It's about the size of the Raspberry Pi Zero. And you could put one of these connectors on the bottom onto it, so that you could actually wire all this and solder it into that and just plug it in on top, and that'd be really compact. I didn't do it for this video because I kind of need a little room, and if I mess up, I don't want to have to be desoldering everything. These boards are real nice because if you make a mistake, you just change your wires around. It's a lot easier than having to pull out the desolder. Got my transistors in place. Next I need to have the resistors. And then the speaker, we're not using a 10 kilo ohm, we're just going to use a 1 kilo ohm for it. So I'm going to put these 10 kilo ohms away so I don't mix them up. We'll put a 1 kilo ohm in place.
So basically, why is it like numbered like 1 kilo ohm, 10 kilo ohm?
Yeah, that's the measurement of how much resistance. You know what resistance is? Resistance is like, say you're trying to run through the sand, okay? If it's really deep sand, or let's say you run into the water, right? If it's real shallow water, it won't be too much, but you should get a little bit deeper, you run, it's going to put a little more resistance, a little bit deeper, it's even more resistance. So that's kind of what these do with electricity. So electricity is trying to get through, and if you have a bigger number, it's going to be harder for the electricity. It's going to burn up some of or use up some of that power. And if you have a smaller number, it uses up a less amount. So we're trying to use up a lot of the power for these LEDs because they don't use much. And we use up a little bit of power for the speaker. Okay, so that's why we used a 1 kilo ohm for the speaker, and we use 20 kilo ohms for each of the LEDs. Okay, so now we've got our transistors and our resistors in. We just want to make sure that nothing's crossing. I don't want any short circuits here. Okay, and everything looks good there. So I think the next thing will be I need to make sure the grounds are connected on both of these boards here. So let me put a ground wire in.
So basically for the LEDs, why? So you know how some is normally just yellow, red, green, and blue.
Mm-hmm.
Why do you have an extra white LED?
Oh, that one's just one I have. I'm not going to use it.
Oh.
Yeah, this one is just, whenever I got them, I got all the colors they had in there, and they had a white one also. So, but yeah, we're just going to use 4 of them for this project.
I was kind of thinking maybe you could use the little white button for like a press start, like a start button.
Well, I do want to have a reset button, but I was thinking about using this one. I'm not sure how much room I have on here. I mean, I think 4 is going to use up a lot of space already, so I think I'm going to use this one for reset.
Okay.
And I don't think we'll use this white one.
So you may use it for.
But we'll see how it goes. Let's get it working, and then we can, if we have some room, we might change it. We can make some changes as we go here.
So if you do like another project with LEDs, you might use that one.
Yeah, or we might make some modifications on this one even. All right, so what I did here is I made sure that the ground, which is the negative, is connected on both. I want this blue line on both of these sides to be the same ground.
Okay.
That's what that wire is doing. Then, I think I'll put the speaker on. So that's actually going from the 5 volt, which I'm going to put on this one, and then the other end just connects directly to, because we don't have a resistor yet, it's just going to connect directly to the collector on the transistor. We'll just plug it right in there. Alright, that's it for the speaker. It's good to go. Now, let's do the LEDs. Okay, so we got red. Let's just start at the top and move away. We got red, blue, green, yellow. We'll just do them in that order. The LEDs are similar. They're going to connect to the 5 volt, and then the other end is going to connect to the collector of their transistor that they're hooked up to. So there's the red. It's done. We've got the LEDs in place. Now we got the switches need to come next. And the switches should be the last piece, and then of course we got to put in the Raspberry Pi. So the way the switches, these are just going to be 3 volts, which is on this panel, to a GPIO pin. So I'm just going to put a row, essentially, and then whatever GPIO pins, I'll just hook them up into those rows. So, and then one more thing I was talking about earlier is I want a reset button. I'm going to use this little button here, and basically whenever you press the button, it closes the circuit between these two short, close together ones. Oh, this switch may not work after all. Alright, so we won't use that switch after all. We'll go ahead and use the white one like you mentioned, Robbie.
Okay.
I just won't use the light on it. I didn't put a transistor in there for the light, so it won't light up, but it'll be used for resetting. Alright?
Okay.
So we'll just have essentially 3 volts, and we'll connect a GPIO pin up to it. Alright, so we'll use this white button for reset. We could just have it lighting up all the time.
But then, what would the color be?
It'll be white.
Oh.
And that'll tell us that it's on. That might actually be useful. So if it's lighting up white, that means it's on. So why don't we do that? That's a good idea. So we'll just send 5 volts straight into this one. And if it's lighting up, that means the system is on and running. And if it's not lighting up, then, well, it's not. Okay. And I just realized that I probably should have put this in the box first. Let's get it working. I can pull these off and rewire them through the box with the holes. But let's get it working before we try doing anything with the box, essentially. Okay, so I think everything is wired up here. All I need to do now is hook in the Raspberry Pi. So I don't need to look anything else. I'm going to go ahead and shut down. Everything is off. Alright, so I need to decide what I'm going to do. Let's just say we're going to do the LEDs will be red 4, green 17, blue 27, yellow 22. And then we'll have the switches. We'll have reset as 10. Then we'll have 9, 11, 5, and 6.
Yeah.
And then for the speaker, we will put it on 13. Alright, so essentially I'm using kind of all the GPIO pins down the side here. Keeps them all together.
So a question I've been waiting to ask is, you know, after the GPIO pin numbers, why do you put a square?
That just so I can count it easy. Yeah, I could have put dots or something. Alright, so remember the pins are aligned like this. So basically you put the pins to the right, and then the top left will be 3 volts, the 2 top right ones will be 5 volts. So this is the configuration here.
I thought for like the squares it was like something special that you do with the GPIO pins.
No. Alright, so this is going to be your 3 volts on this panel down here.
So, quick question.
Yeah.
Why is the board right there that you're connecting all the wires to, why is it called the breadboard?
I'm not actually sure. Maybe because it looks like bread? I don't know. I don't know. Alright, so this should be my circuit. A little bit complicated. I didn't expect it to get this nasty here, but that's fine. This may be a challenge to get in the box, of course, but let's just see if it works. We gotta run some tests on here. Let me check my battery before I start that, make sure I've got enough to continue here. Yeah, so we've got a little bit of battery lift on the camera, so I'm going to go ahead and run some tests. I'll probably stop after I run the tests, and I'll do the programming in a separate video, and then I can just dub them together. All right, or I may post them as part 1 and part 2. We'll decide. All right, so
Yep.
let's go ahead and hook this up, and hopefully we don't start a fire here.
Hopefully.
Let's put my battery in. See if there's any smoke. I don't see anything weird going on. Alright.
And I don't smell anything.
Okay. So this is going to be a little bit of a challenge because everything's backwards now. That's fine. Let's rotate everything here a bit.
I remember one time when we were getting this video ready, you were doing something else with the Raspberry Pi, and there was something that was like hooked over it, and then it started to burn.
Yeah, that was actually was the so I had one of these hubs here, these USB hubs. It was a powered one, and so it had a power cord plugged into it. I had unplugged the power cord from it, and I didn't realize this was an issue, by the way. So we unplugged the power cord from the power outlet, the adapter. So the adapter was unplugged, but it was still plugged into the hub, and the hub was still plugged into the computer. So it was getting power, I guess, from the USB. That's the only thing I could think. And so that was somehow causing that adapter to get really hot and smoky. And so yeah, we smelled it, and it was pretty bad. So
yeah, I was the one that.
Yeah, you detected it, so that's good. Didn't start a fire. Caught it in time, but yeah. So yeah, that's something I didn't realize was actually unsafe. But if you have a powered USB adapter, if you're gonna unplug it from the wall, you want to unplug the power adapter from the hub also. All right, we're back. We ran into a little bit of a problem after the last video. Basically what happened is the Docker that was running on here was not executing running my containers. It kept exiting with a code 139 or something. Eventually found out that even though the RMHF images used to work on here, and in fact I've run some tests before with GPIO pins and whatnot, it's actually stopped working, and I couldn't even run the simple hello world on the RMHF. But I found that the RMEL actually is still working. So what I did is I ended up rebuilding NuPIC for RMEL, and so that should work now. So the other thing that we changed a little bit since the last video is the red and the green LEDs I had wired up a little bit backwards. I fixed that, and also got rid of the this white button. I really don't think that's going to fit in that small box, so I ended up just soldering some wires to this smaller button. We'll use this for the reset button instead of that big white one. We fixed some spelling errors on the box, and that's pretty much it. So now I think we're ready to start programming.
Yeah, and also in the last video, Dad was thinking about adding, like, doing or I was thinking about doing the big one because it wasn't working. So I found a bigger box, but then he found out how to work it, so we didn't need it.
Yeah, so I think we're good now. I think we can run this small one, which will fit a lot nicer into that box, I believe.
Come back.
Alright, so let me make sure nothing came out since the last video. It's been a couple of days.
Yeah.
We were busy with other stuff too, so
Yeah.
so make sure everything's still looking okay. I think everything is good here still. Looks pretty
Mhm.
good.
Yeah, it looks good.
Okay. All right, so let's go ahead and get started. Okay, so what I'm going to do is I'm going to first create a folder for our source code. I'm going to call it Simon.
I found some of my games on there.
Yeah, these are some. So Robbie's been programming in Scratch,
Yeah.
and so a lot of his games are on this one. This
Yeah.
particular SD card I took out of his
I named one Dab.
his Pi. So yeah. So these are some of the stuff that Robbie's been doing. But we're going to create the reverse Simon, or what are we calling it now? The Simon Press Button HTM edition.
Yeah.
Okay. So we're going to make the Simon Press Button HTM edition.
That's a tongue twister.
In this folder, Home Pi Simon. Okay. So what do we want to do? To get NuPIC on here, I've already actually downloaded, so you don't have to wait for it to download. So I've put instructions on the forum for how to get Docker installed and how to download the image. And once it's on here, you can just execute it. So basically the command is docker run -it. That means if I put ITD, it would run deferred, which means it would run in the background. But with IT, I'm telling it I want to run a specific command, and I want to be attached to the process whenever it runs. Then we have -rm. That means whenever I leave the container, I want it to get deleted. I don't need it to stick around. That's what that one means.
I like how you put minus.
Yep. And then we're going to map a device. So for the GPIO pins, there's two things that you need. One is device, and that is /dev/GPIO-mem, and you want to mount that at dev/GPIO-mem. Okay.
It's like
So,
the exact same
yeah,
thing.
so we're taking dev GPIO-mem on the host, and we're making sure it's available also inside the container, is what that means. Then we also need a volume, so -v, and that one is /sys. So /sys, and we want it to be at /sys. So /sys on the host is now available, and /sys in the container.
I forgot. Did you say this in the last video we did? Why we need the hot glue gun?
Yeah, so the hot glue gun, I'm just heating it up because whenever we finish here, we're going to put it in the box, and we might need it to attach things like this button here, for example. It's just there if we need it. If we don't use it, that's fine too. But I just wanted it to be heated up so we don't have to wait for it to heat up.
Wait for 10 hours.
So it's there if I need it. If we don't use it, that's fine too.
Yeah.
All right, and then one more volume I want to mount is, so this folder I just created under Home Pi Simon, this folder, I want to have that available inside the container. And the reason is, I like, on my nice graphical user interface, I want to be able to edit my Python files, so I can edit them on the host. If I had them only in the container, then I'd have to edit them in the container. I'd have to use some like Nano or something. I don't want to do that. So I want to make sure that I have this folder available inside the container as well. So we've got /home/pi/Simon, and I want to mount that in the container at /home/pi/Simon. Yeah. So in other words, I want it in the same place.
Yeah.
So it's easy to find. I know where exactly where
It's
it
like
is.
the exact same thing.
Okay.
With 3 things.
So basically what we've done is we say we're going to run a particular command, which I haven't said what it is yet. And when it's done, I want it to go away. I need to make sure I have this dev GPIO-mem device. I need to make sure I have this sys folder. And I need to make sure I have this Home Pi Simon folder.
When you want it to go, it's like, be gone from me!
Okay.
It's like the Force.
Now the name of the image, and this is also on, I put this on the forum as well. The name of the image is Paul's Code /NuPIC
NuPIC!
:Pi 0.
You get a new pick.
Yeah. Now, yes, funny. All right, so NuPIC, that's of course the HTM. Then the name of the tag is Pi 0. If you're running on the Pi 0W, you need the Pi 0. If you're running on the 3B plus, the bigger
You need
Pi,
the 3B.
no, just put Pi. It's just called Pi. So if you're running the big one, just do NuPIC :Pi. That's the one I was running earlier. That was
Yay, it's pie!
Raspberry Pi. Alright, so if you're running on the big one, you just use the Pi tag, but if you're running on the Pi 0W, you just use the Pi 0 tag. This is the one that's written in, or that's built on the ARM-EL base image.
Making me listen to you saying pie is making me hungry.
Yes, pie. All right.
Especially raspberry.
All right, and then the actual command that we want to run, which is why I had that in my IT. The actual command that we want to run is just bash, which means I want to go into a bash cell. So this should execute if I didn't type anything wrong. We'll see what happens.
10 hours later.
So it's just launching, and we're inside there. So the other problem that we were having before was it wouldn't even get this far. It would just wait for a little bit and then it would stop.
It's like 5 years later.
And if you looked up the exit code, all it would say was 139, which is essentially a seg fault, and it doesn't say any useful information, unfortunately. So if you see that and you're running the pi tag, just do the pi 0 tag.
Pi 0 tag, yeah.
Alrighty, so now we're inside the container and we're ready to code. So if you look, LSAL, we've got the Simon folder. This is the Simon folder right here. So this is where we're going to put our code. We're going to put it right in there. So let's go into there. Alright, and we are now available. We've got NuPIC available to us, and all we got to do is start writing code.
Yay, we get a new pick!
HTML. Alright, so what we're doing here is let me start. I'm going to make some classes. So I think what I'm going to do is I'm going to have a class for each of for the lights, essentially, a class to use the lights.
Kind of like the Simon Swipe, the new one. I think it came out a year ago.
Well, we're not going to have any swiping. We're just going to have button pressing, which is why it's called the press button edition, I guess.
I wish we had swiping.
All right, so so we're just going to have buttons, but these buttons have lights, so I need a class for controlling the lights. I need a class for controlling the buttons. And a class for controlling the speaker. So I'm going to create three
classes.
classes.
That's only 3. What about the last one?
The last what? Last file?
Button.
That's still a button. It's a class for the button. Class for all the buttons. Class for all the lights, and a class for the speaker. There's only one.
For all the speakers! We had 10,000 speakers
We're gonna
here.
do it in stereo. All right, so let's.
Maybe you should make a Halloween mode.
All right, let's start with the reverse Simon, or the Simon press button HTML edition.
That's a tongue twister.
Let's just do that one first. We'll worry about Halloween stuff later. Okay,
Yay.
so we'll need a file for the LEDs. So we're going to led.python.py. We're going to have.
If it's supposed to be LED, why does it say LED?
Nice one. All right, then we need one for the buttons. Button.py.
Yay! On here I spelled
Button.
Button.
Yeah, you had an O instead of a U. It's
Simon Press Button HTML edition.
It's okay. We learned by making mistakes.
Yes.
Okay, so then we need a speaker.
Yay!
All right, we'll start with these. We might need some more. We'll decide what we're going to do as we go. But I think these will be enough to start with. Let's do the LEDs because those are the fun ones. The light up. Everyone loves lights.
Maybe we should make an orange one for Halloween. like there's like an extra small orange button that lights up orange, and then when you press it, Halloween edition.
Yep. Okay. All right. So this is our LED. So we need to have GPIO. So from RPI import GPIO. Okay, so we need that. Then we're going to create a class, and we're going to call it LED. We need to have the initial init function, and that's going to take self. We need to know what GPIO pin it's running on. I think that's it. I think that's all we need there. Okay. So the first thing we need to do is GPIO.setup. Oh, well, actually, we need to hold on. We need to know about the pin later. So let's do a pin self.pin equals pin. All right. So we want to hold on.
You're basically saying the same thing, except it's the self pin.
Yeah. So this pin is just the one that came from the outside, and I want to attach it to the object. So that's what self is. Self is the object. So self pin is equal to the pin that they gave me. Is what that means.
I still don't get it.
You'll figure it out later. Don't worry. So basically, I need to be able to know what pin it's running on even later, not just right here.
I get it a little bit more now.
Okay. So we're gonna do GPIO dot setup. We need to know what pin it is. So self dot pin. And then we want this to be in output mode. So GPIO dot out.
Isn't this your phone charger?
Yeah, that's a USB-C. That's what. Remember, I had to have that for this thing to start. It won't start up by its own. It's kind of weird.
That's really
So I had to put it in there, and then it'll start up, and then I could take it out later, and it'd be fine. But I had to have it in there to start. So we're gonna leave in there. It's actually charging the battery while I have it in there. So while I'm programming, we're not using
Wait,
the
what
battery.
level is the battery?
100%,
How do you know?
because all the lights are on.
Oh.
All right. So we said we want to be an output pin.
Yay.
Okay. And then let's see, what else do we need to do here? That's probably it for now. We need to have a on. So we need to be able to turn the light on.
This
so we
is
can
the
say,
definition of LED.
LED. LED, you know what that stands for? Light emitting diode.
It doesn't stand for lead?
No, it's
Oh.
light emitting diode. Okay, so this is a function we're creating to turn the light on, and I'm going to add something called duration.
I thought emitting started with an A.
Emitting. It begins with E.
Oh.
Okay. All right. So I want to have a duration. Now let me explain why I want that. There's kind of two ways that we're going to light this thing up. One is when I press the button, I want to turn on, and then when I release it, I want to turn off. But the other way is whenever NuPIC is playing the sequence back, it's going to light up a particular input, and then it's going to light up another one, and another one, so on. And I don't want it to have to worry about calling the on function, and then waiting a little bit, and then calling the off function. I want to just say, play it for a little bit of time, and then automatically turn off when you're done. So that's what we're going to do there.
No magic.
So that duration will be, if I want to, I can tell it how long to light up, otherwise it'll just stay on forever.
No, imagine someone like when they first made it and they were like ready, and then they just press the start button and then they just go, try to beat this, boop 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 boop, and they just keep pressing it until it's like 8 a.m.
That's not how Simon works. It'll make more sense. Watch, whenever we get there, you'll understand what I mean. Okay, so basically what I'm saying is I want, by default, I don't care about, I want to stay on until I say turn off. But if I want to, I can pass it a duration, and then it'll only stay on for that long. That's the idea.
What did you just say?
So, if I say I want to turn the light on,
Okay.
and I don't say what the duration is, it's just going to stay on until I tell it to turn the light off. But if I say I want to turn on for 1 second, it'll turn on, and then 1 second later it'll automatically turn off. I won't have to.
So it's like,
I don't have to tell it to.
it's like boop. 1 second later, boop.
Yeah, and I don't have to tell it to turn off. It'll just do it by itself. That's the idea. Make sense?
Why is
Alright,
that
so we're
blue
gonna
like
do-
brown?
GPIO, because it's hot.
Oh.
GPIO dot output, I believe it is. Hopefully I remember that right. And that's going to take self dot pin,
I hope so we don't have to reinstall Docker over again.
and then it is GPIO dot high. Alright, so basically what I'm saying is I want this pin to go high, which means turn on the light essentially.
When you said high, I thought you meant the HI kind of high.
No.
Hi!
So that's what we want to do there. And then
No.
we also need to know if the duration is greater than 0. In other words, if they say they want it to turn off.
So like if someone says like GPIO and then they press turn on and it says hi.
Okay. So no, we're not going to do that.
Aw.
Okay, so the other thing, so I need to have like a timer, and I believe it's in the threading
Get 20
package.
seconds to finish your code.
From threading, import timer. Alright, so in the threading package, we're going to bring a timer in, and I need the timer to tell it when to turn off. So we're going to say t equals timer, duration, self dot off. Alright, so this is going to say after the duration is passed, I'm going to call the off function. That's it for on. Then we're gonna have def off, and it's just gonna be self. And this one's gonna do GPIO.output,
Hey Dad, is this yours?
self.pin, GPIO.low.
Dad, is this yours?
Yes, please
It's
put it
mine now.
away. Please put it away. All right, so we're gonna, when they call the off function, we're essentially just gonna set the output to GPIO low, which means turn the light off. And that is it for our function. Let's do a test. I'm probably gonna need sleep. And that is from time, I believe. So from time import sleep. So this is just to test the class. I'm gonna remove this after I'm done testing. We're gonna do need us to tell what mode we're in. So GPIO.set mode. GPIO.BCM. So BCM is the Broadcom numbering, so that says that the pin numbers that I'm using are the Broadcom numbers, not the, I believe it's called board numbers is the other mode. Okay, so we're going to set that mode, then we're going to create some lights. So let's just see, we have 4 lights, so we'll go red equals LED. Where did I put red? I wrote what my things are. Yes, so I moved red to pin 19. It was originally on pin 4. And the reason I moved to pin 19 is when I powered this up, it was turned on already. So I'm thinking maybe this this Lion hat was actually using pin 4. So I moved it to another pin, pin 19. So hopefully it'll work over there. So we're going to say red is on pin 19. Green is an LED that's on pin 17. Blue is an LED on pin
27.
27, yeah.
I just guessed.
Yellow is
18?
an LED on 22.
Aw, I was close. I was close though.
Okay, so we created our LEDs. So what we're going to do is red on for, I don't know, quarter second, let's say, 1.25. And then we're going to sleep for half a second.
Yay!
And we'll do this for each of the lights here just to test them all out. So green, blue, yellow.
0.5 seconds is half of a second.
Yep.
I always thought it was 8.5 because I thought you put 8.5.
No. 0.5. All right, green. Yeah, I get what you're saying. The 0 looks kind of like an 8, doesn't it?
It does.
Green, blue, yellow. And let's actually, on the yellow, let's test the on function that does not take a duration. Make sure
How many?
Works.
That thing is magical. That glue gun is magical. It's magically doing glue.
Okay.
It's really magical.
All right. Don't be such a chatterbox. You're making me lose my train of thought. All right.
Sorry.
So GPIO.cleanup is what you run. You have to run that at the end when you're done. All right. So what I'm doing here is I'm going to write red, green, blue, yellow. Red, green, blue, yellow. And yellow is going to stay on for 2 seconds, and that's going to turn off. Let's make sure that function works. Dot off. And then we're going to do cleanup, which should allow us to shut down cleanly. So let's just see how this works. Let's see if this works. All right, so come in here. We're going to do Python. We're back inside our container. Python, what I call it, led.py. All right,
What's
so
PY stand for?
Python. All right, so let's see if these light up the way we should get. Red, green, blue, yellow should stay on for 2 seconds. All right. All right, we have an error. What did we do? Has no attribute pi. Okay, what did I do? Oh, pin. That's probably right. All right, let's try again. Should get red, green, blue, yellow, 2 seconds. Red, green, blue, yellow, and none of them turned off, so there's a problem.
No, I like it like that.
Well, it's not working though.
Oh.
Okay. start the timer.
Oh my goodness.
Alright. That, of course.
You're like, what did I do wrong? And then 10 hours later, oh, I didn't set the timer.
That's why you test often. Test early, test often. And if you try to test everything at the end, you're going to have big trouble finding all the problems. Alright, this should work now. Hopefully. Let's see. Yep, okay. And it's not, it did not sleep the way I wanted it to, though.
No.
I think it's because I really didn't sleep long enough here. Let's see.
Put 1 second.
I think I'm working on time scales that are a little bit too fast for this pi 0 probably. So let's just say we're going to give it a second for it to, it should turn off in a quarter second, but we're going to wait at least a second before we move on to the next light. Let's see.
What's quarter of a second?
You can fit 4 of them in a second.
What's quarter of a second?
Yeah, that looks good. Alright, we're in good
Why
shape.
does the yellow stay on longer?
Because I tell it to wait 2 seconds.
Oh.
So I said on and stay on. I didn't give it a duration, see? And I said wait for 2 seconds and then turn on. Okay? Alright, so we're going to hold on to this test. We might need it later, but I don't actually want it part of this class, so I'm going to go ahead and comment it out here. But it'll still be there if I need it. Alright, so we're ready. The lights are working. We have the functions we need there. So let's try the speaker next. Speakers are fun.
No, it's like we're trying to make it soft, and then when we play a sound,
Yeah, I actually don't know how loud it's going to be because remember we put that larger resistor on there, so it's not getting full power. So it should not be full volume, but I don't really know if it's going to be really quiet, if it's going to be loud. We'll see. We will find out here.
What sound are we gonna make it play first for a test? It's the final countdown.
I actually need to look up what frequencies I want to use, but so for now let's so this means the duty cycle. So eventually I'm just going to create a square wave. We'll see how that sounds, but it basically means half of it will be low, half of it will be high. And that's it. All right, so let's create a test for this one too. So we're going to need the sleep function again. So from time, import sleep, small I think. And then we need to say what mode we're running in. So GPIO.setMode, GPIO.BCM. Are you going to do any coloring on the other side, Robbie?
I don't know.
Well, let's see. This one looks way better than that one. I don't know. Alright, you do whatever you want. Okay, so we're going to say we're in BCM mode, which tells us to use the Broadcom numbering like we did before. We're going to create a speaker, so my speaker, cool speaker, needs to have, what did I give it? Which pin it's running on, okay, so the speaker was on pin 13.
Dad. It's me old speaker.
My speaker.
No, it's me.
Alright, anyway, so my speaker, play, and I don't know what frequency, let's try 250, hopefully that's
How about 550?
I don't know what's actually on.
How about 555? The day of the fives.
Well, if it sounds really low or really high, we can change it. Hopefully it's something we can hear. We'll find out. So we're going to play 250, and then we're going to sleep. We need a duration. So what we did 0.25 before, and then we slept for 1 second, right?
Yeah. Imagine if someone did the tempo on a speaker and they put it on on really, really soft, like 1, and then it like blasted their ears and it went, and then they put it on like the highest number they could think of and it went.
Alright, so kind of like we did on the lights, what I'm going to do is have it play the sound 3 times, and then on the 4th time it's going to play it for 2 seconds.
painting right there. Except for that white splotch on it.
Alright, let's see how this works. See what kind of bugs I have now. So Python, speaker, that's a pi. Alright, we prepared for loud or soft, who knows? Find out. That's actually fine.
That scared me when you started it.
Alright, that actually is perfectly fine. It's not too loud.
Can we do it again?
Sure, why not? Speaker is working great though.
Boop, 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 boop. 10 seconds later.
It says this channel is already used. So that's from because I did not do GPIO.cleanup.
Yay!
And this is why you run cleanup at the end.
Why?
Because otherwise it thinks it's already in use and it really isn't.
It's like, no, you're not in use. Yes, I am. No, you're not. Yes, I am.
Let's save. If I run it again, hopefully it's cleaned up now. Yes, okay.
When you did it again, it scared me again.
It's not scary. Okay, so we've got, let's go ahead and comment out our test here. We'll hold on in case we need it later for some reason. Or if I remember how to do things, for example. Okay, so we've done the LEDs, they seem to work good. We've done the speaker, it works great. Now we got the button.
Yay! Didn't we already do the button?
No, we did the lights.
Oh, you mean this button?
All of these buttons.
No, we did this.
We're going to test all of them. All we tested was the lights. We didn't test the actual button.
Oh.
What I want to do is have a callback that all the buttons use, and the callback you'll send it the index.
What's a callback?
Callback is a function to handle the button presses. So I don't want it to write 1, 2, 3, 4, 5 functions. I want to have one function for all of them. But whenever it calls that function, I need to know which button was pressed. And so I'm going to send the index.
By callback, I thought I was going to call the other button and they were going to have a conversation.
No. Alright, so then we need to know what pin it's attached to so we can set it up. And then we also need to have what the callback is. So we're going to say callback.
For a minute, here doing this video, at first I thought we were just alone and we weren't doing a video and you were just teaching me this.
Alright, so, yeah, so calm down. Remember you're on film.
Yeah.
Alright, so. So we'll have this thing called state. So if anytime I need to know what state the button is in, if it's pressed or not, I'll just go to state, and if it is false, that means it's not pressed. If it's true, that means it is pressed.
Which state is the red button in? Which state is it in?
False.
Oh, I thought it was in I thought it was in Texas.
Alright, so we're going to run the test. Okay, button callback.
Yeah, like having sharp nails because when you're taking off stickers, it hurts the underside of your nails. It really hurts.
Oh, I spelled it wrong. E-B-T-N. Okay.
You literally spelled something wrong?
Okay. Oh yeah, I need to set, oops. I need to say what mode we're running in. So.
Are you messing everything up here? No! and ye shall receive.
Alright, so press enter to quit. So this should work now. I should see.
Ask and ye shall
Button 1 was pressed. Button 1 released.
ask if ye shall receive.
Button
Except
2 is
for the
pressed.
video game.
Button 2 received. Button 3 is pressed. Button 3 received released. 4 pressed, 4 released, and then the reset should be button 0. 0 pressed, 0 released. So all the buttons are working. Enter to quit. Alright, so that's it for that test. So we'll go ahead and comment the tests out. And okay. Alright. So that's it. I have all the classes I need. I think at this point, I'm ready to actually begin writing the actual game.
Yay!
Yeah. So Robbie, whenever you're done there, can you clean up the little pieces of stuff that you?
Stickers?
Yep. Thank you. All right. So.
I know how to write in cursive.
That's very good. So get your practice. Yeah, it doesn't count to actually throw them on the floor, so you'll have to pick them up. All right. So we're going to create a new file for the game. I'm just going to call it simon.py.
Simon dot yummy pie.
All right.
Imagine if someone said Simon dot yummy raspberry pie. Yummy raspberry pie.
All right, so we're going to write the actual game now. We have all the buttons and the lights and the speaker are all working.
I have a knife.
Okay, can you put it in the trash bin?
Okay.
Thank you.
I'm collecting the stickers. Thank you for the stickers that I drop on you.
Alrighty, so we're going to need for the game, of course, we're going to need NuPIC, so import NuPIC.
It's not
I'm gonna
it's not
need
ye house, it's me house.
temporal memory.
It's Minecraft. It's now Minecraft.
Alright, so we have to think about how we're actually going to do this game. I'm thinking, first of all, I think I'm gonna not use spatial pooling. I think instead I'm just gonna use pure temporal memory. And the reason is I've only got 4 inputs.
And one more input.
Well, that's not actually an HTM input though. These are the only HTM inputs are gonna be these 4.
What about that one?
It's not an HTM input.
Oh.
So there's only going to be 4 HTM inputs. They're not going to share any semantics. And so so this is kind of the situation where if I was not to use boosting on the spatial pooler, which we'll assume we're not going to, this is a fairly simple program that we're writing, and we have a small number of semantically dissimilar inputs, then all I really need to do is deal with the mini columns that encode just those 4 inputs, and all the other mini columns are never going to be used, so I don't really have to deal with them. So I'm going to just completely avoid the spatial pooling step entirely and focus only on the mini columns that I need to be able to do these 4 inputs. And actually it should be 5 inputs, and the reason for 5 inputs is, think about this. Remember, it's trying to learn a sequence of button presses. So if I started on red, say red and green and then red, let's just say that was the sequence. That's a higher order sequence because the red is in 2 different contexts. So if I did that, whenever I said the second red, it would say red, green, red, blue, for example. When I hit that second red, and if it were to burst, what would happen is it would predict both the blue and the green, which I don't want. And so every time I started the sequence, I would reset it. I would press the red. It would predict blue and green. So what I want to do, I think, is I don't want the first input to be used anywhere else in the sequence. Is what I'm trying to get at. I essentially want an initial hidden input that's not part of the button. It's just going to automatically run it, automatically compute it, and it'll be the first element of the sequence, and it will never be reused later in the sequence. So if it bursts, it's always going to predict the first element in the sequence, the first visible element of the sequence, which in this case is red. So when that many columns for that input bursts, it's going to predict red if red was the first input, yellow if yellow was the first input, and so on. And then after that, if I'm unfolding the sequence, it's not going to burst because it's going to be a specific context for red, a specific one for yellow, etc. So that's kind of the strategy I'm going to do. Is I'm going to have 5 inputs, a hidden one that's used only at the very beginning of the sequence, and then the other 4 will be used to define the rest of the sequence.
Yay!
All right. Anyway, so that was kind of long-winded, but I'm kind of thinking that's how I'm going to do the.
You are the most long-winded winder.
Okay. So we've got temporal memory. We're not going to use spatial pooling, like I said. We're going to have 2 modes. So the game is going to have essentially a mode where it's playing back what it's learned, and it's going to have a mode where I'm adding to the sequence. Remember how Simon works. It starts with 1 input, then it has 2, then it has 3, then it has 4, and so on. So it's basically going back and forth. Where I'm giving it a little bit more information each time it gets to my turn, and then when it gets to its turn, it needs to repeat it back. So there's 2 modes. There's the training mode and then the repeat mode. So I'm going to have a variable called mode, and we'll start it in repeat mode. And why am I doing that? Why would I start in repeat mode? I think what I'm going to do is if I press any of the buttons while it's playing back the sequence, I don't want it to do anything. I want to wait for it to finish before I can start doing more inputs. So I'm going to say I'm going to wrap around. If mode is 0, I'm going to ignore the inputs. And now let me say I'm going to start out in mode 0 and wait till I finish setting up, initializing everything. Then I'll turn mode into 1, and now let me start the game. Okay. Have a seat, Robbie, please. Okay.
How do you fix that?
It's fine. Okay. So I'm going to put in mode 0 so that until I finish initializing everything, then I'm going to put it to mode 1 and I can start doing inputs at that point. Alright, so what am I going to need for this? I'm going to need a temporal memory object.
You're going to need 10 of those.
Let's see, what do I need to give it? Column dimensions. We're going to do 200. So imagine a typical 2048 many-column layer. Each semantically dissimilar input is going to activate about 40 many columns. So if I'm dealing with only the many columns for these 5 inputs, there's an initial 1, 2, and they each use 40 many columns each, then my column dimensions that I can use for temporal memory is 200. So I can say there's 200 many columns. These are the ones that are actually going to change. All the rest of the 2048 are never going to change because I only have this small number of inputs, and I'm not using spatial pooling boosting. So we'll start with just 200 many columns. And then what else do we need? We need to have initial permanents. Say 0.5 and connected. Connected permanent. So what I want to do here is I want to have one-shot learning. I don't want to have to repeat the sequence more than once for it to learn it. And so what I'm setting the learning really high here, where as soon as it creates a new synapse, it's going to be connected. Okay, and I'm going to do some other things on here too to make it, to really bias it toward one-shot learning. Then we're going to have min threshold. We'll set that at 10. That's fine.
I'm getting
Then
bored.
we're going to have, well, you can move on on to something else, but can you come back whenever you think of something to ask, okay?
Okay.
So we set the min threshold to 10. I also need to tell it how many cells per mini column, of course. Cells per column 32. I need to have the min threshold. I need to know the permanence increment. One, that's fine. We're also going to have max new net count equals, I don't know, 32, I guess. And then duration. Something low, like 13. So let me kind of explain what I've done here. Basically, we are saying that if at least 13 synapses are active, we're going to call that above the threshold. We're going to go ahead and put this cell into predictive state. The increment and decrement really doesn't matter too much because we're really only learning one sequence in this game. Max new synapse count, I have that really high. So basically we're going to have 40 active cells that we could potentially connect to, and I'm going to connect to 32 of them. It's a large number. The main thing is it needs to be more than the activation threshold, essentially. Min threshold doesn't matter, it just needs to be low. And then, like I said, I want when the synapses are created, I want them to immediately be connected. So that's why I made the initial permanence and connected permanence the same. And at 32 cells per mini column, that's just sort of the usual configuration that you have here. All right, so that creates our temporal memory. Next, I need to have some input SDRs for each of the inputs. So there's going to be 5 of them. So input SDRs equals NuPIC zeros. We're going to have 5 of them. Type we have to set new 32. Okay, so this basically says I'm going to create 5 SDRs for the inputs. I'm starting them out at 0. They're all zeroed out, and then I'm going to put the ones in next. But basically, I need 5 of them. Each of them need to be as large as the number of columns. So we're using 200. The reason we're using 200 again is that the rest of the 2048 are never going to be active, so we're just going to sort of ignore those because of the way we're setting up our inputs. Alright, so we need to actually create the SDRs, and I'll just create sort of places for them to go. So we can do 4 x in range 5. So for each one of these we're going to create an SDR, so we're going to say input SDRs x So what I'm doing here is I'm creating, so there's, actually it's not input STRs, that's, yes, that's input STRs, sorry. So, yes, so what I'm saying is, yeah, I call these input STRs. So what I'm saying is I want the first input to have 41s here in the first 40 slots. Then the next one to have 41s in the next 40 slots, the next one to have 41s in the next 40 slots, and so on. So basically, I'm giving each of them a block of 40 mini columns, each of the inputs. And from here I need to translate that into active columns. So active mini columns. So for each input I have a certain number of active mini columns. And since I'm skipping spatial pooling, it really matches the input STR. So I can say input columns input columns append set C for CI STRs next. One. Alright, so what I've done here is I've said, there's another way of thinking of an STR. Firstly, you could have all of your whole entire STR with a bunch of zeros and a few of them are ones. The other way is to say, I can just have references to the 1 bits and assume that everything else is 0. So this kind of, I've given a sort of another, this is the same as input STRs because I'm not using spatial pooling, but instead I'm just putting in the indexes to the 1 bits rather than having the full array with the zeros and ones. That's what that does there. It's got two different ways of thinking about the same STRs essentially. Alright, so next, so create everything for the temporal memory. I need to have, of course, the LEDs. So let's just we're going to put everything into an array. Basically an array of 5 elements. Everything's going to be an array of 5 elements, just like I have the inputs, array of 5 elements. I'm going to have LEDs as an array of 5 elements. LEDs X equals LED X. Alright, so we need to tell it what pins these go into. So we need LED pins and one array of 5 elements. And we only have 4 LEDs. So the first one I'm just going to put a pin that's actually not even hooked up. So what did we use the last was 19, we'll say 26. So in other words, if somehow we say light up that LED on pin 26, nothing will happen because that's the initial input. It doesn't have a light associated with it. But then the rest of them actually do have lights. So we've got 19 for red, we've got 17 for green, 27 for blue, and 22 for yellow. So this is going to create an LED for each of those GPIO pins. So that gives us our LEDs. Then we're also going to have tones that the speaker needs to play. So we need tones. And what values I'm going to. Actually, let me look up. I don't really know any good frequencies to use. So where is middle C on here? C4. Yeah, so let's do A through A. So we could do 220 on one end, 440 on the other. Let me write this down. So we have red equals 220, green, blue, and then yellow is going to be 440. So we got an octave here. And then we can do, let's just do C and E is fine. So we'll have green will be 262, blue will be 330. Okay, so we've got our tones. Go ahead and close that. So I'm going to have tones are slot 0 is not used. There is no 0 button that I can press, so in case somehow it comes up, I'm just going to say 0, which will be no sound, essentially. We're going to have 220 for red, 262 for green, 330 for blue, and 440 for yellow. Okay. And then we're going to say speaker equals. So the speaker, let me look at the constructor for that. It just takes the pin, okay, it just takes what pin it's running on. So it's running, the speaker is running on pin 13. Okay. Alright, so we got our lights and our speaker. Now we need a function that's going to play things back. So let's do that next. We'll call that unfold. Okay, so the way I want to play things back is, first of all, I'm going to reset the temporal memory, so nothing will be predicted. Then I'll play that first input, the hidden input, the one that only happens at the beginning of the sequence. And that will predict the next element, which will appear to be the first element of the sequence. And then I'll just play that, which will predict something else, and I'll play that, which will predict something else. I'll play that. We actually keep going until we run out of predictions. And then we'll switch the mode back into input mode and reset. So I think that's how I'm going to essentially do the unfolding. It's kind of a poor man's temporal unfolding. I think it'll work for this game because the way the training works. I think this is going to work for this game. We'll see though. So basically what we'll do is we'll have tm.reset, and then we'll execute the first input, compute, input columns 0. We don't want to learn whenever we're playing back. We want to learn whenever we're in train mode. So I'm just going to say learn equals false. Okay. Then that will predict something. So I need to say predictive columns equals cell. We'll do cell for column I for I in tm dot get predictive. Alright, so what this is going to do is this is going to say for each of the predictive cells, I'm going to take the column that predictive cell's in, and I'm going to put that into an array, basically another SDR that I'm going to use to activate the next element of the sequence. So the predictions are going to become then the next input. The many columns that the predictive cells are in are going to become the next input. Okay, so we'll basically need to run a loop. So while we have predictions, so while in predictive columns greater than 0, so while we continue to have predictions, we need to light up whatever light is involved, so LEDs. First of all, I need to say what is a prediction. So remember we have basically a set of ones and then the next set of ones, so 40, 40, 40, 40 is our inputs. So if we take the first predicted column, divide that by 40, that'll give us the index. So that's actually a nice way to get the prediction here. So we can say prediction equals predictive columns slot 0 divided by 40. Okay. Then we're going to light up the light, so LEDs prediction on, and we'll stay on for a very short while. Now we'll say on for 2.5 like we did before, so a quarter second. We want to play the sound that goes with that, so we're going to say speaker play tones / prediction. And we want to do it for the same amount of time. We need sleep, so time import sleep. Oh, we also need to import all of our classes, so we need import LED, import content, speaker. Okay, so we're going to light up the light, play the sound, sleep for. This didn't work before. Let's try it though, because it seemed like when I changed it to 1, it seemed like it actually was working. So we might have to change this to play 1 every second, but let's try playing 1, 2 a second. Will sound a little nicer, I think. This will be like dun 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 versus dun dun dun. Be a little bit slower. We'll see how it goes though. All right, so play the tone, sleep a bit. We need to actually make the next prediction. So. Compute, temporal memory, compute, input, columns, slot prediction. We don't want to learn. Okay. Basically, again, we're saying we're going to get the many columns that the predictive cells are in. I'm going to create. That's going to become the next input, essentially. Okay. All right. So that's going to go until eventually there's no predictions, and this will say the length of predicted columns will not be greater than 0, and it's going to hop down to here. So once I'm done playing everything back. What I need to do now is reset the temporal memory again. I need to compute the first input again, so that whenever the next thing I type, the next thing I press should be the first element again, and the first button in my sequence that I'm going to put. So we'll compute input on 0. And this time we're back in learn mode. Back to training, so we'll do learn true. And then we let the user start typing in the next the next element in the sequence. So mode will go back to 1. All right. We need to. Let's see how this goes. Then the input mode is going to be in a button callback. So def takes index state. If index is 0. So this means I press the reset button. This will be at index 0. Then what do I want to do? I want to basically have a new temporal memory. I need a new set of columns essentially to run temporal memory on. So we'll do that. temporal memory. Basically, we're going to learn, basically we're going to start fresh. I need to run the first input again. That's always going to be the first input, so I need to compute it programmatically here, automatically. Need to learn it, of course. And somehow we need to tell the user that it's finished. So I think I'm going to flash these actually. So let me do for free. We'll just do a really quick burst. Hopefully, I don't know if it'll work on the Pi 0 W. We'll see. But sleep. No, not for each one. No. So what that should do is it'll blink, do a couple quick blinks to let me know that it's finished setting everything up again. And it'll put it in mode 1. Yeah, whenever this first occurs, I need to not accept any more input, so equals 0. Okay. So that is if we press this button. Any other button, we need to be in mode 1, so we're going to do elif mode equals 1. So in other words, we only accept input from these buttons if we're in training mode. So if mode equals 1, then we're going to say if state. So if the button is pressed, we're going to light up the light. So LED index on, speaker play, index. And then we need to run temporal memory. We need to train temporal memory. So tm.compute input columns index. Please have a seat, Robbie.
You're almost done.
Do you have any new questions? Yeah, we'll be done soon. Alright, so this is basically saying whatever we press, we're going to play that light, we'll play that sound, and we're going to learn it. Okay? And then one more thing, I need to know if it's bursting. Because the reason is, I'm going to basically, if it was predicted and I pressed it, then it won't burst. But when I get to the last one and I press the one after it, that one's going to burst. So that's how I'm going to know that I need to go back into replay mode. So I'm going to basically looking for whenever I'm bursting. So we're going to say bursting is false. And then, excuse me.
I want to use the mouse.
Oh, please, let me finish here. I'm going to run out of battery on my video. So,
You still have 0.5%.
okay, good. So I think I'm almost done here, actually. So basically, if it's bursting, let's see, how do we, I don't remember the command for, actually I know how I can do it. So if, yeah, so if there's more than 40 cells active, then it must be bursting, because if it was predicted, there's 40 mini columns, 1 cell per mini column, 40. So if it's bursting, then that means, that's how I know it's bursting. So, bursting equals true. And that's it. So why would we not begin unfolding here? The reason I did that is I want to know that it's bursting when I press the button. But I don't want it to start playing back until I actually release the button. I don't want it to be like pressing and immediately starts playing things back. It'll be a little bit jarring. So instead I want to know that it needs to start playing back whenever I press the button, but I don't want it to actually start playing back until after I release the button. So I'm going to hold on to this variable called bursting to know that, okay, when you release that button, I know that I need to start playing back. So we go back to else, which means if the button has been released, then we're going to turn off the LED. We're going to stop the speaker. We're going to check if it's bursting. If it is, we're going to set bursting back to false. We're going to set the mode to playback. Can you please sit, Robbie? Thank you. Alright, so bursting is false. The mode is in playback mode. And then we want to unfold. Okay. Alright.
Finally, this open.
Okay, so this is the button callback. If it's index 0, we're resetting. If it's mode 1, we're going to learn the new column. If it's bursting, when we release, we're going to go back into playback mode and do the unfold function.
You've
Okay.
been doing this for over an hour.
Yes, please have a seat. It takes a while to write a game like this, Robbie.
No, I never do that.
Okay, so, and I never actually created my buttons, so let's do that. Button pins equals, what are my button
I
pins?
thought you did.
I did not actually create the buttons. I created the LEDs. I forgot to create the buttons. So we have
Oh.
pin 10 for the reset, pin 9 for red, 11 for green, 5 for blue, 6 for yellow. And then for X in range 5.
I don't think you have any more soda left.
It's okay. Alright, buttons equals an array. We're going to put them in. So buttons dot append button. Well, the button takes an index, so we need X. Takes a pin, so button pins X. And it takes the callback, which was button callback, button CB. Okay, let me see if I missed anything else up here. Oh yeah, I can't do this actually. I can run these.
Do YouTubers get paid?
If they get enough views, then I believe they get paid, probably. But this one probably will not get enough views. But anyway, so all right, let me look through here real quick, make sure we're good. Mode 0, created temporal memory. We have the right dimensions. Created our SDRs. This looks fine. Starting 1 through
I've heard if
0
you get
through 4. Yeah.
I've heard if you get over 1 million subscribers, you get the diamond play button.
Cool. Alright, so we created our LEDs, we pinned them, we put our tones in there, we put our speaker, we created the unfold function, reset, we compute the first one, get the predictive columns from the predictive cells. While we have predictions, we're saying what the prediction is and letting speaker play, sleep, compute with learn off.
How do you
Okay.
say all that?
Okay. Get to the end, we're resetting, starting the first one, go back to mode, blah, blah, blah. We already looked at that,
You should
all right.
say etc. etc.
et cetera, et cetera. Okay. Now, this is quite a lot of code, so let's go ahead and debug it. So,
What's
we have
debug mean?
find problems.
Oh.
We call Simon Pi. See what kind of. Oh wait, we do actually have a problem here. So don't start yet. I actually need to tell it that we're done setting up. Remember, I put it in mode 1. So let's do the same thing we did up here. We essentially light up the lights real quick. blink blink, it'll tell us it's ready, and then we'll go into mode 1. And then like we did earlier, I think we'll do a raw input, press, insert to quit, and then we need to clean up the theme. Alright. That looks a little better. Let's see how that runs. Okay. Y equal, yeah, so for Y and where this from.
Isn't this the computer I use for programming?
This is the SD card. You had one of the bigger ones that you were using though. So I pulled the SD card because the other SD card, I thought maybe it was something wrong with the software, the installation. Whenever I couldn't get Docker to run, so I put this one in because I knew this one was working, and it had the same problem. So this, yes, this is the one that was on your Pi, and I'll put it back on your Pi when we're done. So don't worry about that.
Okay.
Okay, so let's try to run this again.
Hours later.
Okay, what has it got wrong now? So valid syntax.
That's a lot of code. How'd you type all that?
Alright, so it blinked. Press enter to quit. Okay, so I think we're we're ready to go. So we'll start with red. Okay. Local above variable mode reference before assignment. Ah, okay, okay. Okay, blinks. So it did not. Okay, let's see what happened here. Oh, okay, I never actually trained it, okay, to start with. Interesting. Okay, so I need to do that. Yeah, it's not that either. Oh, of course, it's calm for cell, duh. I'm not looking up a cell, I'm looking up a column. Kind of obvious. Okay, let's try that again. Thanks. Everything's ready. Okay, that's a little jarring. It actually played the input immediately after I released, so actually I think I'm gonna wait a little bit. Before I start playing back, so it's not quite as jarring. Okay. so that's working. Let's see if our reset works. Okay. Blinked for us. Let's give it a shot. Okay, do another reset. We'll start with a different color this time. Alright, so everything is working. I think at this point we've created the reverse Simon game. Now I think it's a matter of actually putting everything into the box. So I'll go ahead and see how we're going to do that. Hey everyone, we're back. The power ran out on my camera and didn't realize it, so we missed a little bit. Not too much has changed though, so I'll show you what I did, and then we'll continue where we left off, and we'll put everything into the box and actually build out the game and try it out. Okay, so the couple things that you missed were at the end of the Simon game, I made it shut down a little bit differently. So I actually have a try and a finally. So basically, instead of expecting us to press enter, we're not actually going to have a keyboard hooked up, so I just need it to loop. And so that's going to just sit there looping until it gets a second, in which case it's going to catch an exception, which will then execute the finally and do the GPIO cleanup. Okay, so this is how we're going to run it. And the other thing I did is I added a service that's going to start automatically whenever the Pi comes on. And so that way, whenever you won't have to have it hooked up to a monitor or anything to figure out how to get the game to start. It'll just start automatically whenever it boots up. So the way the service looks is I created this script here. It's called start.sh.
What does SH stand for?
Shell. It's a shell script.
Oh.
And basically it just goes into the Simon folder and it executes Python on the simon.py file. Alright, so this is going to run in the container. I remember this folder here is mounted in the container, so it has access to run this file.
What's the libpyc?
Yes, that's a compiled version of the Python file that I wrote. It runs faster apparently. Okay, so then I wrote an actual service here. So let me pull this up. This is the actual service that will run whenever the computer fully starts up, or it's one of the services that run whenever the computer starts up. And basically what it's looking for is the Docker service to be running. So it's going to come on after it. It requires it. And it basically has an execution command that just says Docker run, and it runs the shell script. You'll notice that I don't have the -IT on this, and that's because we not have a TTY input, which is essentially what this keyboard is, the keyboard input. We don't have keyboard input, so I took that off. The rest of that command is just what we saw earlier, and I'm running the shell script, which is going to execute Python. It puts us in a particular work directory, and if it fails, it's going to restart, and it's running as user Pi. That's essentially all that says. So this is going to allow the game to start whenever the Pi starts up. And that's it. So that's the only thing you missed. We're going to pick up from there, and we're going to put everything into the box at this point. So first, let me shut down the Pi.
Why you shut it down?
Because we're going to unplug everything and we're going to build it into the box. What do you need?
Scissors.
Let me draw where I want to do stuff before we start cutting.
Okay.
Alright, wait
But
for
I
this to
wanna
shut
cut.
down. Okay, we'll see if it's something that you can do, because it's going to actually be in the middle, so it might be hard to do. What you could do is you could cut these off for me. Can you do that?
Mhm.
Cut them nice and clean, as close as you can, okay? And be careful not to hurt yourself.
I didn't open these.
Are they too tight for you?
Okay. Is it? Hold on.
better ones over there?
Mhm.
Alright, go ahead and use those. Just be careful with it, okay?
It's really short.
That's fine, you can stay like that. No, no, not these, not these. Just these.
Oh.
Yeah.
Why?
Yeah, we do need a top on it. But I don't want those in the way when we're cutting our holes. Make sense?
I guess.
Okay.
I'm just trimming out a little for any strands.
Robbie, can you also look in the drawer over there and see if there's any clear tape?
Hold on.
Yeah, I don't know why it's taking a while to shut down here.
Man, it broke.
Okay, shut down now, so we'll wait till the light stops blinking. Okay,
Oh,
wait,
what do you
so-
want again?
Can you look and see if there's any clear tape in that drawer over there? Alright,
This one?
so we're going to unplug all the wires and hopefully the
Are these good?
battery will power it. This one, yeah, that'll work, thank you.
I just magically found it.
Great, and so the battery is now powering it, so that's great. That's what we need. Get all this out of the way. We don't need any of these.
We tested it after the second video.
Yeah, it's working good, but we're going to put it in the box now, and so that we'll have the actual final product. Okay, I think that's good enough, right?
Trying to trim it.
Yeah, but I don't want the battery to run out or something.
I'm almost done. Hold on.
Okay. I think this would have worked out a little better if I had hacked the power, the Lion hat, so that I could actually move that switch out and have it on the outside. That would have been a nice mod. And there's another mod I would have liked to do where I don't have to plug this in to sort of get it started. For some reason you have to plug that in, and then when you pull it out, then it can run off the battery. So a couple of things I would have changed probably on this, but I think it's actually gonna be a pretty fun game. So let's try it out. Robbie, you want to start or you want me to start?
I'll start.
Okay. Alright, let's see how long of a pattern you can get before it gets confused or you confuse,
It.
or it confuses you. Yes.
Yeah. So it's ready?
Doesn't matter which one you press first. Anyway.
Oh my. This one? Okay.
That was probably the last one. Can you remember?
How did it How did it?
I think it has a good memory, Robbie. Yeah, we optimize it for one-shot learning, so it has a very good memory.
Okay, how about...
Ah, you started a new pattern, huh? Alright, my turn.
Yeah.
Alright.
Reset.
Let's see if the reset works. Oh, I did make a mistake on the reset. It's actually resets twice when I press the button. Once when I press it and then once when I release it. That was a little bit of an
It's
error in
fine,
the code,
it's
but it's
fine.
fine. It still works. Alright, let me start with something other than red.
How about blue?
Yeah, let's start with blue.
I knew you were gonna do that.
I didn't know I was gonna do that.
I can see your finger. It's like a song. Green. Aw, it's close. Do a new pattern. After this one, do a new pattern.
I don't remember.
Oh, you.
It's too long now. I can't remember it.
You did it right.
Okay.
Do a new pattern.
That's enough for me.
Do a
Okay.
new pattern.
Okay, we'll do a new pattern. We'll do one more and then we'll end the video here. I think this was a great success. It seems to be working great. I'll put the source code up on GitHub for anybody who wants to dig into how I wrote the code for this. This is a fun project.
One, two, three, four. One, two, three, four. One, two, three, four.
Alright, let's get some wrong.
1, 2, 3, 4.
Ooh, what's he gonna do? Ooh, I learned a new pattern. Okay. What? What? Okay, you killed it. Oh, what?
No! This happened to us when we were practicing.
You totally confused it, my friend. What is it gonna do now? Oh, it's trying to... Okay, fine. Is it good? Oh, it's good now. What? It says no. 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 I want you to play those. Those are better. Yeah, now it's happy.
No, this! This happened to us when we were practicing.
Okay. I think we'll end the
No,
video
it's this one.
I think we'll end the video there. Yeah, this is a very fun project. I'll
See
see y'all
ya!
later. Bye bye, guys.